In today's problem, we'll be exploring charged particle motion in electric and magnetic fields. This is something you've seen in everyday life, maybe long ago in the past when we had televisions before flat screens and before plasma screens. They had these old larger televisions, which were basically just boxes in which electrons were shooting down. And so the electron was going down this tube, and where it was going was dictated by electric and magnetic fields, which could change its trajectory. And rastering that image across the screen could produce an image that we see on the television. So we're going to be taking a look at a similar situation, much more trivial, but again, the similar concept will be at play. So let's go ahead and take a look at the problem statement. Okay, so in this problem we have a situation in which a charged particle is moving under the influence of both an electric and a magnetic force. And the problem is asking us to find the magnetic field. If there were only an electric force, which is given in the problem, naturally the electron would deflect in some direction. So we're imagining that the only way to make it go in a straight line and not deflect is to have a compensating magnetic force. And the question is, what field would give us that particular force to cancel out the electric force? So the plan for the problem will be the following. What we're going to do first is, we'll first kind of get an intuition by looking for the field direction. And as always in these types of problems, when you want to find the field or the force direction involving magnetic fields, you have to use a right-hand rule. So we're going to use a right-hand rule, kind of work backwards to find the field direction. All right, and so once we have that, we also know that the forces have to cancel out. So by setting them equal and opposite, we can find out the field. So the next part will be to set the magnitudes of the electric force and the electric field equal to one another. And then based on that, we can find the magnetic field magnitude itself. All right, and then finally, the problem gives us a kinetic energy. And we know that we're going to have somewhere in here velocities because the force depends on the velocity. So we'll use a kinetic energy to find velocity and then plug that in up there. So the last part will be to use a kinetic energy to find the velocity. And then we can probably plug that into this formula to find the magnetic field itself. So to get started, let's first determine what direction the force from the electric field points, and that'll give us an indication of where the magnetic force points, and then from that we can find the field direction. So in this situation, we have an electric field pointing downward. Now that's not the same direction the force points, because the force from an electric field equals a charge times the field itself. So in this case, because the charge is negative because we have an electron, the field points down, meaning that the force will have to point upward. So I'll write that up here as an electric force pointing upward. So of course we're going to need we're going to need a magnetic field to point downward to compensate that. So the magnetic force, not a magnetic field. So the magnetic force has to point down to compensate it. Now, what we need to find out is what direction does the field point in to make that force. So remember, the force can be found from knowledge of both the field and the velocity of the charged particle. So what I want you guys to do on your own is to determine which direction does a field point using the right-hand rule. So you want to line up your V, B, and your thumb with the force, line them up to get the force pointing down, and then determine which way the field points. Now the problem asks for the minimum magnetic field that's needed. And what that indicates actually is that there's more than one magnetic field that will give a downward direction of the force. So if you found one direction for the magnetic field, try to go a little further and find a couple more directions that would also work. Take a minute now and pause the video if you need to. Okay, so applying the right-hand rule, in the right-hand rule, the velocity of the charged particle always points along your index finger, the magnetic field points along your middle finger, and the force points along your thumb. So lining those up here, we have the index finger pointing along the positive x direction, and we want the force to point along our thumb, so the magnetic force points downward. Naturally, the field direction will be given by the middle finger, and so as we kind of rotate our hand, the field direction will point in the positive z direction, as you can see here. Now this only applies for positively charged particles, because that's what the right-hand rule is used for. In this case, we have a negatively charged particle, an electron, so we actually take the positive z direction and just reverse it. So whatever you get with the right-hand rule, find the opposite. Positive z now becomes negative z. So we have an indication that the magnetic field should point in the negative z direction to give a force that goes downward upon the electron. Let me just kind of draw this picture from a top-down view. So what I'm going to do is kind of rotate this so that the y-axis comes out of the screen, the z points down, and the x goes in the rightward direction. So that'll look like this. And then y comes out. And so like I was saying, the field direction should point in the negative z direction. So in that case, That'll look like on this diagram like this. So this is the magnetic field. Now the problem was actually asking for the minimum magnetic field magnitude to give this particular deflection. And that indicates that there's maybe more than one magnetic field that can produce this particular force pointing downward. Now how does that occur? Well, we know that the force of the magnetic force is given by the following formula. It's QV cross B. And this is a cross product. And so whenever you have vectors that are parallel in cross products, the cross product of two parallel vectors is 0. And so what we can do is actually to this magnetic field is if we have the velocity of the charged particle pointing to the in the positive x direction, then we can add any sort of component to this field pointing in that direction because that won't contribute because that particular component crossed with V will be 0 because they're parallel or anti-parallel. So what you can do is take that field and then just add components in the positive x direction. And the force will still be the same because those components do not contribute because they're parallel to the velocity itself. So actually any field that has some negative z component, no matter what the x component is, will still produce a downward deflection in the negative y direction. But the question, of course, is asking for the minimum magnetic field, and this is why they said this, because there's more than one answer. The minimum magnetic field will be the case where you have no components in the x direction, so that'll be the one pointing directly in the negative z direction. And so the direction for this particular problem will be in the negative z direction. Okay, so that's the first step. We found the direction of the magnetic field. Now we need to find the magnitude of the field. And we're going to use the fact that the forces must compensate one another, so they're going to be equal and opposite, electric and magnetic force. So setting them equal, we have that the force of the electric field equals the force of the magnetic field, and then just plugging in the formulas. Again, we're taking magnitudes here. So you can take the magnitude of all the factors one by one. The magnitude of Q is just going to be its absolute value. The magnitude of a vector, just write as the vector without the vector thing on top. And then the same for the left-hand side. Now the magnitude of V cross B, the magnitude of any cross product equals the magnitudes of the vectors times the sine of the angle between them. So it's V times B times sine theta. Okay, so this theta is the angle between V and B. And you can look at your picture and figure out what that angle is. And so I'd like you guys to go ahead and carry this out from here and try to determine what the magnetic field magnitude is. And use the numbers given in the problem so you know what you may be able to find what the angle is. The velocity, you might have to use part 3 here. Use a kinetic energy. Work backwards and find the velocity. Plug those numbers in and try to get an actual number in Teslas for the magnetic field. And we'll come back and take a look at that in a moment. And what we get here is that the magnetic field equals the electric field divided by the velocity. The angle here is 90 degrees because we have velocity pointing in the positive x direction, magnetic field pointing in the negative z direction. Those are 90 degrees apart. Sine of 90 is 1, so that cancels out. And then finally, you can use a kinetic energy is 1/2 mv squared. Solve that for the velocity since you know the kinetic energy, you know the mass. Plug that in there. You can find the final value for the magnetic field. And the value you should get is the magnetic field magnitude is 3.4 times 10 to the negative 4 Teslas. And the question is asking for the magnetic field in unit vector notation. So this is a vector. We do need to find its vector components. We have the magnitude here. We know it points in the negative z direction. So the final answer is quite simple. The negative z direction has a unit vector, which is minus k. So the final answer is minus 3.4 times 10 to the negative 4 in the minus k direction, and the units is Teslas. All right, so that's a magnetic field that will produce the particular force here that would cancel out the electric force and keep this electron moving in a straight direction. So let's take a look at the summary. In this problem, we were asked to find the magnetic field that would direct an electron in a straight path given a uniform electric field. We first found the proper direction for B using the right-hand rule, and then we set the magnetic and electric force equal to find an expression for B in terms of the electric field and the velocity. Finally, we used the kinetic energy to solve for the velocity and plug that in to find a numerical answer for the magnetic field. I hope this is a useful example on how to solve for missing quantities in situations involving both electric and magnetic fields and forces. And if you have any comments or questions, please leave them on the link next to the video, and we'll see you next time.